Okay, in the previous video we derived the Langevin equation, and here we're going to look at some solutions to it and some consequences of the Langevin equation. Okay, Langevin equation with inertia, that is. So here's our Langevin equation, which is there. Okay, mass times acceleration equals all the forces. The forces are drag, okay, which is proportional to the minus velocity, it opposes the velocity. Random forces plus all the other stuff. Okay, and m here is the mass of the particle, gamma is the drag constant, r of t are the random forces, or m times r of t are the random forces. Now, and f other is all the deterministic stuff. So let's neglect all these other forces, get rid of those for the moment. And if we do that, well, all the m's cancel, and we get v dot is minus drag constant times v plus r of t. So you've got a particle which is going along. This is the acceleration. The acceleration is given by something times the velocity in the other direction plus the random kick, random stuff. Okay, so let's try and get a handle on what this equation means by averaging it. Can we say something by averaging it? So this particular video is going to be a little bit mathematically, I wouldn't say complex, but the equations come pretty thick and fast. Okay. So we know that v dot is the same as x double dot. Let's take this equation here and write x dot for v and x double dot for v dot, and this multiplied through by x. All we do is take that equation, multiply through by x, and we get this. Okay. Now, there is a nice identity you can write down, which you can prove yourself in not very long, which is that x times x double dot is a half of d squared x squared dt squared minus x dot squared. So if you just expand the right hand side, you'll find you get the left hand side. Just differentiate it. Okay, so if we use that identity in there, okay, we can then get the following equation. The right hand side stays more or less the same, and we get this thing on the left hand side which looks like this. Okay, and so that becomes our equation, this particular thing. We'll put that on the next slide as well. Okay, there it is. Okay, now we seem to have got an equation here which is just equally crazy and can't be solved in any particular way. So what are we going to do now? Now we're going to do an ensemble average. Okay. Now, if we do an ensemble average, we can use equipetition, which you should know from a previous course, that a half m, x dot squared must equal a half kbt. Every quadratic degrees of freedom gives you a half kbt in the average, and so we can get that particular thing. We do an ensemble average of this whole thing. That term is easy. We actually know what the answer is. Okay, for our particle. We also know that the average of x times rt, which would be this term here, is given by average of x times the average of r of t. And the reason for that is because these random bombardments have nothing to do with x. They're totally uncorrelated. So we can just split the thing up. The average of that becomes the splitting of the average of that times the average of that. Okay? And the average of r of t must be 0 because bombardments on the left and bombardments on the right must be the same. So this term averages out to 0. That's 0 now. Okay, so we know that term and we know that term. Okay, and then we're going to let alpha be defined to be the average, the ensemble average of dx squared dt. Okay, just take a hold of copies of it and just find out what the average value is. Okay, and this means our equation here becomes much simpler. It's half d alpha to t minus kt on m equals minus gamma on 2 alpha. Okay, because dx squared to t is there, and this is d alpha to t here, which is the derivative of that. Okay, so that's what our equation becomes. I'll write that out in the next slide. So this is our average equation of motion. Remember, alpha here is defined to be dx squared dt average. Okay, so that's our equation of motion and average. Now, that equation we can actually solve because it's just basically exponential decay plus another bit. Okay, and so when we get that, we will get an equation which basically says that alpha is equal to 2kt on m gamma plus d exp of minus gamma t. Okay, and if you're different, you can either see that by inspection, or you can just differentiate and plug the thing in. You know, d alpha to t, that term goes to nothing. We're going to get d exp minus gamma t, so we're going to get a minus gamma coming down there, and you'll find out that works. Okay, so here d is some constant. Okay, we're not normally interested in this particular term because it's the transient initial term for our particle, and it decays rapidly. So it's going to zoop like this, decays away rapidly. So we can just ignore that term. Okay, and so in the long term, what happens is that alpha is just equal to dx squared to t. That's the definition of it, which is d dt of x squared. Okay, which is going to be 2 kt on m gamma. Okay, and so what we end up with is x squared is equal to 2 kt m gamma on t. Okay, so we just integrate this, and we end up with that particular equation. And this tells us something which we will see later on in the course, which is that if a system is undergoing a random walk with no external forces acting on it, nothing except random forces, the distance squared it goes, which is that, is proportional to the time. Okay, it's not like an ordinary ballistic particle, say moving at constant velocity, where the distance is proportional to time. The distance squared is proportional to time, and this result is one of Einstein's results for a random walk, even though it was also derived for lots of other people. So x squared is proportional to time. So that's the equation of motion on average. That's what we get from that. We get a very this I cannot emphasize enough how crucial this particular result is, and we will do that a lot more later on when we actually do random walks. But the size of your random walk is proportional. The size squared is proportional to the number of steps. In other words, the size, how far you go, is proportional to the square root of the number of steps you take, or proportional to the square root of the time. Okay. So let's go back now and try and solve the Langevin equation without doing any averaging. Okay, again with no extra deterministic forces. Our equation of motion is just this guy here. dv dt, acceleration is minus gamma v plus r plus the random part. Okay. Now this, of course, is a stochastic differential equation, and we don't want to go into all the horrendous problems you can get onto when solving stochastic differential equations. There are whole courses on that at ANU, and we're not doing them. Okay, we're not teaching that course. So let's try and solve that. Now the easiest way to solve that, you can do it by inspection, but you can also just use this substitution. V is u e to the minus gamma t. Okay. And if we do that, what we find out is that du dt is e to the gamma t r of t. So you just take the equation and it converts into that. By the way, this particular methodology I'm teaching you here, it's not an examinable part of the course. We're doing it to show you what's going on, but no one would expect you to guess that to solve that you do this substitution. That's not reasonable to guess that. Okay, so this side here is just du dt. This side is only a function of t. So we just do, du equals blah, 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 dt. We'd integrate it, which is what we've done here. Okay. And so we get a solution. ut is equal to whatever it started out at 0. 0 to t times the integral of r exp of gamma t. And then we can, because we've already made the substitution, we can substitute back, and we can get how the velocity depends upon time. So we've actually solved the Langevin equation for the case where we have no weird external forces, and that's the solution. This solution is just here. It's pretty damn simple, and we'll go into that in a second. Okay, so here it is. Now the first term, which is this bit here, is the effect of the initial velocity, and it decays rapidly as e to the minus gamma t. So you don't have to wait very long. If you wait for a time which is, if gamma t becomes, say 10, in other words, t becomes 10 1 on gammas, it's basically 0. Okay, it's gone away. Okay, The second term is a bit more subtle. It decays as either minus gamma t, but then it's also got a gamma t in the integral. Okay, so it's got all these random kicks, random force kicks, which in fact r of t is a random acceleration in this case, because there's got the factor of m, which has been taken out. But each of these random forces is weighted by e to the gamma t dash. Okay, and so recent kicks dominate. Recent kicks have time up to t, and they're much more likely to dominate. Okay, so what does that tell us? So this is our formal solution. Now let's take an ensemble average. Let's not ensemble time. Let's just take an ensemble average. We know that v of t is equal to 0, because if you average over an ensemble for the different sort of copies of the system, it's got this as much probability of going left and right, this as much probability of moving left and right. So that, you know, that's equal to 0. Okay. So let's try and use that to find the magnitude of the random forces, because I really haven't told you anything about how big these random forces are. Okay. Now we know the random force is mRt, and we also know for random forces, something which I didn't emphasize before, which I'm going to tell you now, is that the correlation function between the random forces at times t1 and t2, average, the average, so that's a correlation function there, is given by some constant times delta t1 minus t2. What that means, this delta function means, is that if t1 and t2 are equal, there's a strong correlation, but if t1 and t2 are not equal, the times are different, the correlation is 0. Okay, the random forces at different times are not correlated. We just don't know what the hell c is. Okay, so let's start with our solution, which is here, and find the average value of v squared t. Okay, let's try and do that. Well, if we start with our solution and we square it and then we average, so let's square it first. I should have averaged this here. Okay, then what happens? Well, we get something that looks like this. We get this squared looks like this. Okay. Now, in the limit as t approaches infinity, so we're going to take a long time limit, we must get what would be the ensemble average. The time average and the ensemble average become the same. Okay, so we must get v squared t must be kt on m. Okay, in the very large limit of large times. Okay, if you ensemble average and time average become the same. Okay, so we know the left hand side in a limit of very large t. Okay, right. So the first term, however, if we do the limit of very large t, this term is 0, because that just makes everything diminish. Okay, the second term is also 0, even though it's got this gamma t thing here, because the average of all these, left and right are the same as far as thermal kicks go, so that must be 0 as well. So this whole term is 0. Okay, and the final term is just this thing here, which is written RT prime, the average of that must be equal to what we explained before for this thing, which is the c, the constant, times the delta function. And so the final term we can actually evaluate. Just do that integral. That integral you can do, and if you do it yourself, because the delta function gives you one integral and the other bit is an exponential, we find c on 2 gamma, and we know that must equal left-hand side. And left-hand side, we told you before, must equal kt on m. Okay, and we already know, well, we don't already know this, but we'll see it later on when we do some other ways of looking at this problem. We don't know it yet, but there's other ways of looking at this. So, what do we have about the random forces? We know the average of the random forces is 0, because left and right kicks are the same, and we know the kind of variance is given by this. Okay, the correlation between times t1 and t2 is this. And we've actually derived how big the random forces are, 2kt on m, which for a sphere, we can write like this, like that. Okay, with the viscosity here, radius of my sphere, temperature, and where this thing here, d, is a diffusion constant. Okay, and this here is this Greek letter squiggles is the mobility. It's one on the mobility. Okay, so a lot of constants floating around here, but effectively what we've done is we've derived how big the random forces are. Okay, so now we know roughly how big they are, and their mean is 0. Okay, so this shows us something important, that you get random forces because C here has got a T in it. Okay, and therefore the random force is proportional to the square root of temperature. Okay, so this is a result which is due to Einstein, and it shows us that the random forces MRT have a magnitude proportional to the square root of temperature and also to the square root of the friction coefficient. So the other thing we can see back here is that the magnitude of these things, C, in other words, square root of C, which is the magnitude of the random forces, also has something which depends on the square root of the viscosity. Okay, that's the square root of the friction. Okay, so there's Einstein with Mr. Langevin there. Okay. All right, so this is one way of expressing the so-called fluctuation dissipation theorem. It tells us something pretty weird, okay, that the size of the random bombardment suffered by a particle depend on the viscosity of the medium. Okay, so how viscous the medium is gives you a handle on how much you're going to kick, how big the kicks are from all the other particles. The fact that the random bombardments depend on the temperature seems sensible, but the dependence on viscosity is something which I don't think anyone would have guessed until Einstein came along and showed that was the case. This is one of those things Einstein did and think, well, it's almost a miracle. Okay? All right. So now we know the average of the random forces, what their variance more or less is. But what we don't know is the distribution. If I tell you for a set of probability distribution, I tell you, okay, I know what the average is and what the variance is, or the standard deviation is. That still doesn't tell you what the distribution looks like. It's not, and I'd like to know what the distribution of random forces are. If I'm going to put a Langevin equation on a computer, I need to be able to tell you not just averages and means of the distribution, but I want to be able to know what the forces are in detail. What's the probability distribution for the forces? Okay, and this is easy because of something called the central limit theorem, which we will do later on. Okay, but the central limit theorem tells us that if you have a whole lot of random stuff added together, that in almost all cases, when you add random stuff together, you get a Gaussian distribution. In other words, a bell curve, one of these x minus x squared times some constants curve. Okay, the standard bell curve thing. So it's Gaussian. Okay, so we actually know now how the forces are distributed, the random forces for the Langevin equation. Okay, we know the random bombardments have mean 0. They have a variance which is proportional to that, and they are Gaussian. So we actually know the whole distribution. Now, given that, you might be tempted to say, oh, well, that means I can write down the distribution for these random forces. The distribution must be that. That's our Gaussian distribution, where sigma is this thing. But this is rubbish, okay, because this thing here isn't even dimensionless, so you can't write this down. You can't have exponential something that's not dimensionless. And the reason why it's rubbish is that R of t is a stochastic time series. We would need really to write down the probability of the functional R of t, which would be something like that. And that involves doing functional integration, functional differentiation, and functional calculus. And we will do some of that later on, but not for some time in this course. Okay. And that's where we will end this lecture. And next lecture, we will go on to do the Langevin equation, or next video, without inertia. Okay, and that's where we will use it to do computer simulations, because that's where it's normally used in computer simulations. Okay, thank you.